Hello everyone, today we'll talk about the solution to the problem most stones removed with same row or column. So, at a single step, we can remove a stone if there is still a stone in the same row or the same column. And in particular, if we think about the strategy for removing those stones, we'll see that there might be a chain of stones that we'll remove. So we remove one, then we remove another, which is no longer necessary, but maybe it was necessary to remove the previous one. So for instance, we can imagine a situation where there is a stone here, a stone here, a stone here, a stone here, here, and so on. And we can take everything except for, let's say, this stone, or maybe this stone. But we can, let's say, take this one, then we can take this one. It's no longer necessary to keep this one possible, so we can take it. Now we can take this one, sort of eating the snake from the tail. And of course, in that chain, the last link, well, it's impossible to take it. There is nothing in the same row or the same column remaining. And of course, it doesn't have to be a chain. It can be a cycle like this, for instance, and still from the cycle we can remove 3 of those 4 elements. And more generally then, if we separate the stones into groups based on connectivity, so whenever 2 stones see each other, they are in the same group, then from all of those groups, it's easy to see that we can take everything except for a single stone. It's not true that any stone that we want may be the stone that we leave, but still, or maybe, no, I think it actually is true. But anyways, there is a way of taking the stones in such a way that only 1 stone remains. And in particular, we've seen that, for instance, if we have leaves here, then we can take those leaves. If we do not have any leaves, so everything is on a cycle, we can take something, break up that cycle, maybe then we have some leaves. So if we take this one, then we can take either of those ones because now they are leaves. And that leaves us with this final element. So at the end of the day, we have to count the number of islands. That's one way of looking at it. To count the number of connected components in the graph, and from all of those connected components, we know that exactly 1 final stone will be remaining. So all the other stones can be taken. So the solution is just to create the graph. So we just create the graph by looking if the stones are connected, so they have exactly 1 of having the same row or having the same column. And if so, we add a bidirectional edge between those 2 stones. We remember if we visited all the stones, at first our result is equal to the number of stones. And now whenever we see a new stone that is not visited, we know that this is a start of a new group. So we remove 1, we subtract 1 from our result, and we go, in this case, by a simple DFS. So we'll have a stack implemented as a list. It starts with the current node on that stack. And while there is something on the stack, we visit all its neighbors. Of course, if they were not visited previously, we mark them as visited, we add them to the stack. So we visit all the stones that can be seen and have not been removed previously by the stone that we're looking at. And at the end, we can just return the result.